All right, sounds like there are, emails. Okay, so it's becoming clear that I am, that I need to put a little more time into checking my email. Yeah, the final grades are not in any way determined yet. I have no way of telling you what, not no way of telling you, but essentially the final grades will be determined from what your score distributions are after I look at everyone's grades. I can only say that I will never curve you down. So the A will be like 90 or above or easier. So yeah, no, I will never curve you down. Okay. So any further questions? Okay, so last time is the final curved. So at this point, what is going to happen is everyone's going to take the final. I will put in your grades into the machine as I've described, and I will see what the grades are. And then my answer is, I might curve, I might not curve, but I will never curve you down. That's all I'm going to say about the grades. And yeah, if you have finished your corrections for midterm 2, please just send me a PDF. That'll be fine. Sounds like y'all had more questions than I anticipated. Okay, so last time, I just want to kind of bring up something helpful. So last time we showed, so we're starting to do some counting, and we're using the product rule, which is for combinatorics, essentially saying if there are a bunch of different ways, if you can break up a task into a bunch of different subtasks that you have to do, and then there are n1 through nk ways to do each of the subtasks, you just multiply all those numbers together to get the total number of ways of doing the full task. Okay, last time we showed that if you have a set S of cardinality n, there are 2 to the n subsets of S. So essentially we're saying the power set of S is of cardinality 2 to the n. Can anyone kind of briefly remind me what the argument was for proving this statement? Right, we made a bijection between subsets of S and bit strings. Namely, we wrote out all of our elements in a row of length n, and then a bit string below that string of elements will, if it's a 0, you don't include that element in the subset. If it's a 1, you do include that element in the subset. What I want to briefly do is just mention that this result can also be proved via induction. We could also prove this result using induction. I don't want to go all the way through this because I kind of have a lot that I want to talk about today. But the idea is, let's assume that we've already done the basis step. So assume for all sets of size of cardinality k, then the size of the power set of S is equal to 2 to the k. So now take a set S with k plus 1 elements. The idea is you should remove one element from your k plus 1 element set. So we're going to remove this one. We'll call this element the S sub k plus 1. And then what I claim is that Well, after I've removed this element, I've got some set of cardinality k, right? Here, this is a now, so the set S minus the set minus the element k plus 1 is a set of cardinality k, right? Well, this isn't a claim. My claim is that all subsets of S are either of the form say A, which is a subset of S minus this last element, Sk, or they are some A union the extra element for some A. Subset of S set minus k plus 1. In other words, what I'm saying is, if I want to understand subsets of my bigger set of size k plus 1, I can first understand all of the subsets of my smaller set, and then I can either say, well, this on its own is a subset of set S, or I could include my element into this subset. So for each subset A of S minus an element, I get two subsets of S, namely A or A union my extra element. So we get 2 times the size of P of S set minus Sk plus 1, which is equal to 2 times 2 to the k, which is equal to 2 to the k plus 1. This was a little sketchy. I just wanted to remind you that there are probably multiple ways that we can prove these identities in combinatorics, and induction is often a useful way to think about it. So here, the point is, my claim is, you can understand subsets of S as being subsets of a smaller set, and then you either include or don't include the extra element. Does that at least kind of make sense what I'm trying to do here? Well, okay. It's not so important. We already know how to prove this using bit strings, so that's fine. Okay, are we good? Shall I move on to another counting example? Okay, cool. Let's do one more product rule thing. How many functions are there? How many injective functions from a set of size m to a set of size n? Okay, so a first question, if m is greater than n, are there any injective functions from a set of size m to a set of size n? So if m is greater than n, there will be 0. So, Catherine, that would be the correct answer if I didn't have the injectivity description. But let's consider, so let m be less than or equal to n. The point is, I could list out all of my elements in the domain, and so let me do a picture. Right, here's my domain set, say, and here's my range set. Oh, I need to make my range set bigger. So the point is, I do indeed have n choices for where I send my first element m, my first element here, right? I could go 1, I could go here, I could go here, I could go here, right? I've got n choices for the first element. But how many choices do I have for the second element? Yes, I have n minus 1 choices for my second element because the injectivity condition says the second element cannot map to this thing. So there are n minus 1 things where this element can go. So there's n minus 1 options for the second element to map to. How many options are there, or how many ways are there to choose the image of the third element? Yeah, n minus 2, all the way down to, so for instance, if I only had 3 elements, then I'd do n times n minus 1 times n minus 2, and this would be the answer, right? I had n choices for where to map the first one, I had n minus 1 choices for where to map the second one, and I had n minus 2 choices for where to map the third one. In general, it's going to be n times n minus 1 times n minus 2, all the way down to n minus m plus 1, right? So essentially, this is just, I can think of this as n minus 0. So if I have m elements, I need m steps, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to m. And so the number will be n minus m plus 1. So it'll be n factorial exactly if n is equal to m. Well, here's the plus 1 is because, let's say m has 1 element. Then the answer is just n, right? If m has 2 elements, L elements, then it's n times n plus n minus 1. There are 2 choices, but the first one is n. The next one you subtract off 1. If m has 3 elements, then it's n times n minus 1 times n minus 2. So you see, I'm not subtracting off 3 here, I'm subtracting off 3 plus 1. Yeah, on the homework, if they don't make the condition that the function be injective, then that's an easier thing to count, because then you can repeat. Yeah. So here, this is a reasonable way to write out this number, but you could also write it, so I think the subtraction is incorrect, Val, but it should be division, right? This should be n factorial divided by n minus m factorial. So that all these extra terms, n minus m dot dot dot, these are divided out, right? Val, are you happy for why it's division instead of subtraction? Yeah, perfect. Okay. So I just want to point out that these expressions appear naturally in the product rule because we're just asking how many ways can I do each successive step? And then you multiply them all up. Okay. Any questions here? Okay, so I think we're pretty comfortable with the multiplication rule or the product rule. Now I want to do a brief example of the sum rule. So sum rule. If a single task can be done in either n1 ways or n2 ways, so yeah, then it can be done in a total of n1 plus n2 ways. So the product rule was essentially saying, I'm going to break my task down into a sequence of tasks, and I need to do task n1 and I need to do task n2 and I need to do task n3, et cetera, et cetera. So the product rule is coming from these ands, basically. For a sum rule, it's like, I can either do this or this. For instance, an example here would be, once again, on the topic of dressing myself, let's say I have 3 t-shirts and 5,000 button-up shirts. Now, I do not subscribe to the style of wearing both a t-shirt and a button-up shirt together. So the question is, Q, how many options do I have for shirts? And it's just the sum rule. I just add the numbers together because it's either a t-shirt or a button-up shirt. There's no and, right? If these were pants and button-up shirts, then I'd have 3 times 5,000 because I need to first pick a pant and then pick a button-up. But here, since it's an or, either I wear a t-shirt or I wear 5,000 button-ups, or one of 5,000 button-ups, then it's just a sum. 5,000 plus 3. How many options do I have for shirts is what the question says. Sorry, the handwriting's getting really bad at this stage in the game, huh? Okay, so the sum rule is kind of really basic, and it only becomes interesting when it's used in conjunction with other counting tools, but I'll do one more example anyways. Let's say the math department needs a representative, needs, let's say, needs a representative who can be either a student or a faculty or a staff member. Let's say that there are 100 students and like 37 faculty and 18 staff. How many ways do we have of choosing a representative? Exactly, we just sum them up. 100 plus 37 plus 18, which is going to be 155, right? Yeah. Okay, so the sum rule is telling you something kind of very simple, but we still need it. I'm happy to hear that. Any questions on these brief examples that we've done? Okay, now let's move on to something a little more interesting. I really want to get to the pigeonhole principle today, so I'm going to do like 2 more examples here. And then pigeonholes. Yes, perfect. Okay. So slightly more interesting is the inclusion-exclusion principle. So the inclusion-exclusion principle is technically, just like all these things actually, is something about sets. So on the level of set intersections, here's what the inclusion-exclusion principle says. It says, so I should probably draw pictures for this. So the inclusion-exclusion principle says, if I want to count the cardinality of a union of two sets, A1 union A2, this is going to be equal to, well, it's going to be equal to A1, the cardinality of A1, plus the cardinality of A2, but I need a correction term, right? It's not always the case that the cardinality of a union is equal to the sum of the cardinalities of the two individual sets, right? Why not? Why is this not enough? They could share elements, exactly. There might be an overlap of A1 and A2. And when I count this, I have counted all the elements in the union how many times? Yeah, I've counted them twice. So what I need to subtract off is the intersection. A1 intersect A2. So now, when I just had this, everything in the intersection was counted twice, once as part of A1 and once as part of A2. And now I subtract off one copy, so now everything is counted precisely once. So essentially the sum rule from above is the inclusion-exclusion principle when the two sets are disjoint, namely a button-up is not a t-shirt. But if I start trying to count things where there's an intersection between the two sets, I need to possibly subtract things. So here's my example for inclusion-exclusion. How many bit strings of length 9 have either start with 1, 1 or end with 0, 0, 0? How do I compute this? So first, we should find one of these numbers at least, right? Yeah, so I don't need to, well, yes, sure. 2 to the 9th divided by 4 is one way to think about it, but I would rather think of it as just 2 to the 7th because the first two choices are made for me. I have no option about what to choose for the first two coordinates, but for the remaining 7 coordinates, 3, 4, 5, 6, 7, 8, 9, well, I have 7 choices to make. So 2 to the 9th divided by 4 is not wrong. It's correct, it gives the right number, but I would rather just think of these two as already have being chosen, so I have 2 to the 7 choices. So I have 2 to the 7 ways to choose a bit string that starts with a 1, 1, 1. And how many ways do I have to choose a bit string that ends with 0, 0, 0? Yeah, exactly. I have 2 to the 5 ways of, wait, I think 6 here, right? 9 minus 3 should be 6. Yeah. So this is my number of ways of choosing the first set. Here's my number of ways of choosing the second set. However, what's the intersection? Well, all of the things inside here have been counted twice. I've counted them once in here and I've counted them once in here. So I have to subtract off a copy of 2 to the 4th, which is all the ways of choosing a bit string that both starts with 2 to the 11th and ends with, starts with 1, 1 and ends with 0, 0, 0. So this is the inclusion-exclusion principle. I have to subtract off the intersection. Is this okay? Why 2 to the 4th? 2 to the 4th is the number of ways I can choose a bit string of length 9, which starts with a 1, 1 and ends with a 0, 0, 0. So as you've seen, I've written out such a bit string, and now I have exactly 4 choices to make, namely whether a 0 or 1 goes in the 3rd coordinate, a 0 or 1 in the 4th coordinate, a 0 or 1 in the 5th coordinate, and a 0 or 1 in the 6th coordinate. So 4 choices, and each choice has 2 options, so I get a 2 to the 4th. Good question. Any further questions? It's incredible how we've already spent a half hour. I can't believe how time goes. Okay, I want to be done with this basic counting, and I want to move on to the pigeonhole principle. Are you with me? Shall we? Pigeon time. Okay. So this is cool. This is way more fun. Okay, here's the pigeonhole principle. The pigeonhole principle states the following. If you have k pigeonholes, I think there's a D. Is there no D? Can someone confirm, please? No D. Ah, okay. Okay, anyways, pigeonholes with a G. If you have k pigeonholes and k plus 1 or more pigeons, and all of the pigeons will roost, must go in some hole. There is at least one pigeonhole with 2 or more pigeons. This is essentially saying, here, I'm saying that I have some function, right, from a set function f. So here's my set M of pigeons. I've got a bunch of pigeons. And here I've got a set N of pigeonholes. Pigeonholes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to have 7 pigeonholes. The point is, if I make some function from M to N, some element of N has to be hit by at least 2 elements of M. There's no possible way that I can have a function from M to N such that every element of N has 1 or fewer preimages, right? Are we okay with what the pigeonhole is saying? It's just expressing this failure of a function to possibly be injective. If a function can't be injective because the preimage is bigger than the domain, any function must map two of these elements to the same element over here. We okay with that? Okay. So now we can start proving some really cool things. So let's first prove, let's show that any integer n has a multiple with only ones and zeros in its digits. So you pick any integer, and I claim that there's any integer n. I claim there's some integer k such that n times k only has ones and zeros. No other digits appear in its digits. What a weird thing, right? How do we prove it? Indeed, we will prove this by magic. And indeed also pigeons. They go hand in hand, as I'm sure you've already seen. Okay, so here's the proof. We will take n plus 1. So n is the integer. We will take n plus 1 numbers, and they're going to be very special numbers. The first one, a1, is just going to be 1. a2 is going to be 1, 1, or 11. a3 is going to be 111. a4 is going to be 1111. And then we're going to do that all the way up to n plus 1, which is whatever number you get when you put n plus 1 ones back to back to back. Are we clear on what my sequence of numbers is? Okay. So now I will examine each of these numbers, ak mod n. How many options are there mod n? Well, if you're mod n, ak mod n, it's either going to be equal to 0, 1, 2, all the way up to n minus 1, right? These are the possible answers for an integer mod n. N possibilities. Do we agree that there are n possibilities for any integer modulo n? Okay, but I have n plus 1 integers, and when I perform the modulo n operation, there are n options. What does the pigeonhole principle tell us? Yes, the pigeon. So by the pigeonhole principle, there must be an AI and an AJ with I not equal to J, such that AI is equal to, or yeah, AI mod n is equal to AJ mod n. well, I should have the parentheses around here. What does it mean that AI is equal to AJ mod n? They're congruent, which means what about n? So what does it mean for two numbers to be congruent? So n divides AI minus AJ. It also divides AJ minus AI. But AI minus AJ, so assume I is greater than J, so that AI minus AJ is positive. But AI minus AJ is going to be a big string of ones minus a smaller string of ones. So AI minus AJ just looks like some number of ones and then some number of zeros. Namely, it's in exactly the form that we demanded. N divides a number which is purely in terms of ones and zeros. It's even more special than that. It's a collection of ones and then a collection of zeros. Kind of cool, huh? Which part of the last bit? So do you agree that by the pigeonhole principle, I must have two of these numbers which have the same modulus, modulo n? So then you agree that for whichever two are the same mod n, I must have n dividing AI minus AJ? Do you agree with this step? Okay, but now I actually examine what my AIs and AJs are. And let's think about what is A4 minus A2? It's 1, 1, 0, 0. What's A5 minus A3? 1, 1, 0, 0, 0. Yeah, the pigeonhole principle works here because I have n plus 1 integers, and I'm reducing them modulo n, for which there are n possibilities. So the pigeonhole principle is what forces there to exist an I and j that are different but equivalent when I take mod. Any more questions about this? Okay, let me do another example in my 10 minutes that I have left. 10 minutes is fine. Okay. Next, let's do the following. Assume that I have 5 points, P1 through P5, which are inside Z cross Z. So these are points inside the real plane. Who knows how they're spaced out? They're arbitrary points, but they have integer coordinates. Okay, so that is P1 is equal to x1, y1, etc. P5 is equal to x5, y5 with all xi, yi in Z. Okay, now we will show that at least one line segment joining Pi to Pj has an integer valued midpoint. So that is, in this picture, this looks like it's at like, I don't know, -10, -7, right? And this point is at, I don't know, it looks like it's at 12, -2. The point is, if I join these 2 points by some line and then I take a midpoint, there's no need for this midpoint to land on an integer, right? For instance, if I look at the 2 points 0, 0 and 1, 1, well, the midpoint of 0, 0 and 1, 1 is 1/2, 1/2. So here, clearly, it's not the case that if I have 2 points which are integer valued or have integer coordinates, that the midpoint of the line intersecting them has integer coordinates. But I claim that if I have 5 points inside the plane that have integer coordinates, I must have at least one line segment joining some pair of them which has an integer coordinate midpoint. How do we prove this? Show that at least one line segment joining pi to pj has an integer valued midpoint or an integer coordinate midpoint. Yes, exactly. What we really need to look at are odd and even x and y values. So the midpoint of the line segment joining pi to pj, which I'll write as this kind of bar, pi, pj, is, what's the first coordinate of the midpoint? Well, it's going to be xi plus xj divided by 2, right? It's the average. And then the second coordinate of the midpoint will be yi plus yj divided by 2. When is this thing an integer? This thing is an integer when xi plus xj is divisible by 2, or in other words, xi plus xj is even. So my question is, if I demand xi plus xj to be even, what does that mean about xi and xj separately? Exactly, they have the same parity. So in order for xi plus xj divided by 2 to be inside z, xi and xj must have the same parity. Okay, what are all the possible parity values for my integers pi and pj? Well, the options are, I could either have, these are the options for the point pi. It could either have an even coordinate and an even coordinate. It could have an even coordinate or an odd coordinate. It could have an odd coordinate and an even coordinate, or it could have an odd coordinate and an odd coordinate. But I have 5 points. What does the pigeonhole principle tell me? Right. By the pigeonhole principle, since I have 5 points and 4 options for pairs of parities, right? That's these things. These are pairs of parities. I must have some I not equal to j, and pi and pj have the same parity for both coordinates. So the midpoint of pi, pj has integer coordinates. Yeah, that's possible. It's possible that all the points could fit one option, and then it's doable. The point is, if I challenge you to give me 5 points, even if you try your best to ensure that I could not have integral midpoints, you won't be able to succeed. It's true, all the pigeons can always go to one hole if they want and be very cozy together. But that's not the power of the pigeonhole principle. The power of the pigeonhole principle is that there's no way that you can avoid having at least 2 in the same pigeonhole. Does that make sense? Any question about this proof? Well, I mean, somehow we've already passed 50 minutes, and that's a class. So any questions? Have a nice weekend. I probably have failed to respond to a bunch of your emails. I should do that. But are you? Yeah, we're definitely learning new things on Monday. Can't stop, won't stop. Yep. Have a nice weekend, everyone. Anything that I cover should be available to ask on the final, but remember, on the final, I have to cover a lot of material. I have to test you on induction. I could test you on cardinality. I could test you on equivalence classes. I could test you on modular arithmetic. So, you know, you shouldn't, I can ask you questions about this combinatoric stuff, but no, the final should be evenly spread. I can confirm this. We have covered chapter 1, chapter 2, some parts of chapter 4, some parts of chapter 6, chapter 5, and chapter 9. That's 6 sections that we've covered. There will definitely be at least one problem from each of those chapters. So there. So, I mean, the recommendation that I can give you is that doing problems from the book will be a good preparation in any given section. So here's what we've covered in this class. We covered chapter 1, we covered chapter 2. We did these almost entirely, right? We covered chapter 4, sections 4.1 and like 4.3. This was like primes, GCDs, stuff like that. We covered 5, this was induction, 5.1 and 5.2. We covered 6.1, 6.2, 6.3 next time, right? This is what we're doing right now. And then also 9.1 and 9.5. Yeah. This is kind of a rough picture of what we've done in our class, right? So I can guarantee you that there will be at least one problem from each of these sections on the final. And then I would guess that my extra problems will be taken from the newer sections. So Yeah, 4.3. This is a 3. You just, you know. Yeah, 4.3. I was gonna say you can't read, but really that's a defense mechanism. Sorry, my handwriting is so terrible. Yeah. Have a nice weekend, everyone. And see you all on Monday.
Did you say that you had office hours today? I checked on the syllabus and it said that you didn't.
I don't have office hours today, but if you want to meet with me to discuss like midterm 2, I could do that.
Okay. Is that over? Is that you mean for today?
Yeah, so I don't have office hours today, but it's okay if we meet like now, if now works for you.
Now does work. However, I have not. I have looked at the midterm and started taking notes about what I've done wrong, but I haven't like finished doing that. So I didn't want to waste your time.
Okay, well, I also have office hours on Monday. That also
Okay.
works. Also, I should stop recording. But yeah, I also have office hours on Monday if you think that would be more suitable.